Optimise technologies, electrical and mechanical innovations. Introduction. Optimise technologies, electrical and mechanical innovations is a comprehensive exploration of the transformative shift from traditional utility systems to intelligent infrastructure. In an era defined by rapid urbanization and climate instability, this book serves as a blueprint for the next generation of engineering, where safety, efficiency, and sustainability are no longer optional, they are the core of design. The text bridges the gap between theoretical physics and real-world application, detailing how passive safety systems such as non-conductive mesh shielding and active energy harvesters like cryodynamic Arctic factories and solar-integrated roadways can be woven into the fabric of our cities. Key themes of the work. Safety through containment, reimagining high-voltage distribution to eliminate live wire hazards through advanced multi-layered sealing and aerated dielectric catchment systems. Infrastructure as an amenity, transforming standard urban fixtures, like traffic lights, into climate-responsive shelters that provide public refuge from extreme weather while monitoring environmental health. Energy generation reborn, exploring the frontier of distributed power, from kinetic energy harvesting in subarctic thermal gradients to dynamic wireless charging roads that power electric vehicles in motion. Systems thinking, moving away from isolated components toward a holistic, interconnected smart grid that responds dynamically to human needs and environmental changes. By synthesizing breakthroughs in materials science with human-centric urban planning, Optimise Technologies offers a visionary yet practical guide for engineers, city planners, and students dedicated to building a resilient, electrified future. 1. The ground-level shift, the case for foot-activated pedestrian interfaces. For decades, the standard for pedestrian safety has been a singular, hand-operated button, often dubbed the beg button. While functional, this design assumes a specific type of user, one with free hands, a certain height, and the physical ability to apply pressure with their fingers. The emergence of the foot-activated crossing switch represents a fundamental shift in urban design, moving away from standardized utility toward inclusive universality. The hygiene imperative, post-pandemic urbanism. Perhaps the most immediate benefit of a foot pedal is the elimination of a high-touch surface. In a post-COVID-19 world, public anxiety regarding fomite transmission via inanimate objects remains a significant factor in how people navigate the city. Pathogen mitigation, pedestrian buttons are notorious magnets for bacteria and viruses. By moving the interaction to the shoe sole level, cities can drastically reduce the transmission of seasonal flus and other communicable diseases. Public perception of safety, beyond actual biology, the foot pedal offers a psychological nudge. It signals to the citizen that the city is prioritizing their health, potentially increasing the willingness of residents to choose walking over private transit. 2. Designing for universal accessibility. True accessibility isn't just about complying with a checklist, it's about removing friction for the widest possible range of human experiences. The full hands scenario, parents pushing strollers, grocery shoppers carrying heavy bags, and commuters juggling umbrellas or luggage often find reaching for a traditional button cumbersome or balance threatening. A foot pedal allows for hands-free activation without breaking stride. Mobility aid integration. For individuals using wheelchairs or walkers, a foot pedal can be positioned to be activated by the footrest of a chair or the base of a walker, providing an alternative for those with limited upper body dexterity or reach. Inclusive sizing. Children and shorter individuals often struggle to reach buttons placed at the standard 3.5 to 4 foot height. A ground-level interface democratizes the ability to request a crossing signal. 3. Enhancing the cognitive flow of the pedestrian. In urban planning, friction refers to anything that slows down or complicates a journey. Traditional buttons require a pedestrian to stop, pivot, and use their hands, a series of micro-actions that break the natural gait of walking. Seamless integration. A foot pedal allows a pedestrian to maintain their forward-facing orientation toward the crosswalk while activating the light. This keeps their eyes on the traffic and their body prepared for movement. Tactile feedback. Foot pedals can be designed with robust mechanical feedback, a click felt through the shoe, which is often more discernible than the faint beep or light of a hand button, especially in loud city environments. Durability and maintenance in harsh environments. From a municipal standpoint, the foot pedal offers surprising mechanical advantages. Hand-operated buttons are prone to button mashing and vandalism, such as being jammed with gum or adhesive. Mechanical resilience. Industrial-grade foot switches are designed to withstand significant weight and pressure, making them less susceptible to the wear and tear of high-traffic intersections. Climate adaptation. In colder climates where pedestrians wear heavy gloves, traditional buttons can be difficult to feel or press. A foot pedal is easily operated by a heavy winter boot, ensuring the system remains functional regardless of the season. The aesthetic of the smart city. Finally, there is an undeniable element of modern urban identity. Implementing foot-activated technology signals that a city is forward-thinking and invested in human-centric design. It transforms a mundane piece of infrastructure into a conversation piece, reinforcing the idea that the city belongs to the people who walk its streets, not just the cars that drive them. 2. The upward gaze, unbent neck, revolutionizing overhead work with Prism vision glasses. For millennia, the act of working overhead has been synonymous with strain. From Michelangelo craning his neck to paint the Sistine Chapel ceiling to modern-day electricians wrestling with conduit above, the human body was simply not designed for prolonged upward gazing. This inherent ergonomic conflict has led to a litany of musculoskeletal issues, reduced productivity, and increased safety risks. The conceptual Prism vision glasses represent a paradigm shift, offering a future where the ceiling is viewed not by contortion, but by simple, straight-ahead vision. The scourge of cervical strain and repetitive stress injuries. The primary and most debilitating issue addressed by Prism vision glasses is the prevention of neck and back injuries. Tradespeople who routinely work overhead, a vast and essential segment of the global workforce, are disproportionately affected by chronic pain and conditions such as cervical spondylosis, degeneration of the spinal discs in the neck, tension neck syndrome, chronic muscle pain and stiffness, pinched nerves, compression of nerves in the cervical spine, shoulder impingement, often a secondary consequence of awkward neck and arm positions. By allowing the user to maintain a neutral head and neck position while viewing their overhead workspace, these glasses could dramatically reduce the incidence of these debilitating conditions, extending careers and improving quality of life for millions. 2. Enhanced precision and quality of work. When one's neck is craned and muscles are tensed, fine motor control inevitably suffers. The ability to work with a comfortable, natural posture translates directly into improved accuracy and craftsmanship. Electricians and HVAC technicians, installing intricate wiring, conduit runs, or ductwork requires precise alignment. Viewing the work directly and comfortably allows for straighter lines, more secure connections, and fewer errors, reducing costly rework. Drywall hangers and finishes. Achieving perfectly seamless drywall joints and smooth finishes on ceilings is an art form. Maintaining a comfortable head position ensures steady hands for taping, mudding, and sanding, leading to superior results. Painters, eliminating neck strain means steadier brushstrokes and roller application, especially around edges and fixtures, preventing drips and missed spots, and ultimately yielding a more professional finish. Plumbers, working with overhead piping, especially in tight spaces, demands careful attention to detail for leak-proof connections. A clear, comfortable view allows for better assessment and execution. 3. Significant boost in productivity and efficiency. Every moment spent repositioning, stretching a stiff neck, or taking a break due to discomfort is a moment lost in productivity. Reduced fatigue, less physical strain means tradespeople can work longer, more focused periods without needing frequent breaks to alleviate pain. Faster task completion. The seamless visual access to the work area eliminates the need for constant head tilting and awkward maneuvers, streamlining the execution of overhead tasks. Optimized workflow. With a clearer and more comfortable view, workers can plan their movements and sequences more efficiently, reducing wasted motion. Elevated safety standards on the job site. Working overhead often involves operating power tools, handling heavy materials, and navigating obstacles while looking up. Any distraction or discomfort can lead to dangerous errors. Improved situational awareness. While focused on the ceiling, the peripheral vision of the ground below and surrounding colleagues or equipment can be compromised when looking straight up. Prism vision glasses allow the user to maintain a general forward orientation, potentially improving awareness of their immediate surroundings below the work area while still seeing the work above. Reduced risk of falls. Workers on ladders or scaffolding maintain better balance when their head and neck are in a neutral position, significantly lowering the risk of losing balance and falling. Enhanced tool handling. Operating drills, saws, or other tools overhead becomes safer when the user is comfortable and can maintain a stable posture, reducing the chance of accidental slippage or injury. Expanding the horizon for specialized trades. The applications extend beyond the most obvious construction and maintenance roles. Audiovisual installers, precisely mounting projectors, speakers, and running cabling in ceilings. Network technicians, working with server rack cabling in elevated data centers or installing overhead network infrastructure. Archaeologists, restoration experts, examining delicate frescoes or structural elements on ceilings in historical buildings without physical strain. Arborists, potentially useful for close inspection of high tree canopies, though modified for outdoor use. Manufacturing assembly, for production lines requiring overhead assembly or inspection of components. The Prism vision glasses are more than a clever optical trick, they represent a profound investment in the health, productivity, and safety of the skilled trades. By literally shifting the gaze, they promise to unlock new levels of comfort and efficiency, transforming strenuous overhead work into a task performed with ease and precision. The future of overhead work looks up, without ever having to crane a neck. 3. Passive containment systems, non-conductive mesh shielding for pedestrian safety. In the hierarchy of electrical safety, elimination and substitution, such as undergrounding, are preferred but often cost-prohibitive. For existing overhead transmission lines in high-density areas, a secondary layer of protection is required. This chapter explores the concept of aerated dielectric catchment systems (ADCS), a specialized non-conductive mesh designed to intercept falling live wires before they reach pedestrian zones. 1. The physics of the catchment mesh. The primary engineering challenge of a safety mesh is balancing mechanical strength with aerodynamic permeability. Non-conductive materials, the mesh must be fabricated from advanced polymers like aramid fibers, Kevlar, or high-strength polyethylene. Because these materials are non-conductive dielectric, the mesh itself does not become energized if a live wire rests upon it. Aerodynamic permeability, to prevent the mesh from acting like a sail during high winds, which could put immense stress on the supporting pylons, the design utilizes a specific open weave geometry. This allows wind to pass through with minimal drag while maintaining a grid size small enough to catch a cable and its associated hardware insulators, clamps. 2. Preventing direct contact and grounding. When a high-voltage wire snaps, it carries massive kinetic energy and lethal electrical potential. The mesh serves two roles. Mechanical arrest, it physically halts the descent of the wire. The mesh is often designed with controlled stretch properties to absorb the impact energy, preventing the wire from bouncing or whipping into nearby structures. Insulation gap, by holding the wire several meters above the ground, the mesh maintains a crucial air gap. This prevents the wire from touching the pavement, thereby eliminating the risk of step potential and touch potential for pedestrians walking below. 3. Impact on grid protection systems. A secondary advantage of a mesh catchment is that it facilitates more reliable fault-to-ground detection. Fault creation. In many systems, the mesh is supported by a grounded frame. When the live wire hits the mesh and sags slightly, it is designed to eventually make contact with a grounded, static, line or the grounded pylon frame. Instantaneous tripping. This intentional short circuit ensures that the utilities protection relays detect the fault and to energize the line in a fraction of a second. Without the mesh, a wire might hang suspended in the air, a high-impedance fault, where it remains energized because it hasn't hit a grounded object yet. 4. Urban design and implementation. Integrating safety mesh into an urban landscape requires a multidisciplinary approach. Visibility and aesthetics. Using translucent or sky-colored fibers can reduce the visual impact on the city skyline. Maintenance. The mesh must be resistant to UV degradation and bird nesting. Regular inspections using drones can ensure the integrity of the weave without requiring power shutdowns. Zonal application. These systems are most effective in high-risk corridors, areas where power lines cross over sidewalks, school zones, or major intersections where the density of human life is highest. Summary of benefits. Feature. Function. Dielectric fiber. Prevents the safety net itself from becoming a hazard. Open weave. Reduces wind loading and prevents structural failure of pylons. 4. The intersection shelter. Reimagining traffic infrastructure as urban refuge. In the modern metropolis, the wait time at a pedestrian crossing is a universal experience of friction. Pedestrians are often stranded on exposed corners, vulnerable to driving rain, blistering UV exposure, and the urban heat island effect. This chapter proposes a shift from purely functional signaling to integrated pedestrian shelters (IPS), transforming the humble traffic light pole into a multi-purpose sanctuary. 1. The anatomy of a climate-responsive crossing. Traditional traffic lights are designed for vehicles, but an IPS system flips the priority toward the human experience. The core design elements include the cantilevered canopy, extending from the main vertical mast. A lightweight, transparent or semi-opaque wing provides a 3 to 5 meter radius of protection. Hydrophobic surface coatings. To prevent water from pooling or dripping onto pedestrians, the canopy uses lotus effect coatings that shed rain instantly toward a discrete drainage channel inside the pole. UV filtration. Utilizing polycarbonate or tempered glass with built-in UV absorbent interlayers, the shelter reduces sun exposure by up to 98%, providing a cool spot for pedestrians during summer heat waves. 2. Microclimate regulation. An intersection shelter isn't just a roof, it's a localized climate modifier. Radiant cooling, heating. In extreme climates, the vertical pylon can house radiant elements. In summer, water-cooled internal pipes integrated with city grey water lines can lower the ambient temperature under the canopy by several degrees. Wind buffering. By using perforated side panels, similar to the non-conductive mesh discussed in previous chapters, the shelter can break up high-velocity wind gusts without creating a high-pressure trap that could destabilize the structure. 3. Smart infrastructure integration. Since traffic lights are already connected to the city's power grid and fiber optic network, they are the ideal bones for additional public services. Dynamic lighting. The underside of the canopy can feature soft, recessed LED lighting that changes color or intensity based on the crossing signal, e.g., a gentle green glow when it's safe to walk. Emergency intercoms and wayfinding. Integration of high-resolution digital maps and emergency, blue light, buttons into the base of the shelter. Air quality monitoring. Sensors at breathing height to collect data on vehicle emissions, helping cities optimize traffic flow to reduce pedestrian exposure to pollutants. 4. Safety and visibility challenges. Engineering a shelter at an intersection requires solving the visibility paradox. If a shelter is too opaque, it creates blind spots for drivers and pedestrians. Challenge. Engineering solution. Driver line of sight. Use of high-clarity structural glass or slotted designs that disappear at certain angles. Structural integrity. Deep pile foundations to account for the increased wind load created by the canopy. Crowd management. Flared canopy designs that encourage flow rather than bottlenecks at the curb. 5. The kinetic kilowatt, the evolution of solar-charged roadways. For decades, roads were passive slabs of asphalt, static grey ribbons designed solely to bear the weight of commerce. In the transition toward a post-carbon economy, the solar road reimagines the street not as a cost of infrastructure, but as a distributed power plant. This chapter examines the architecture, physics, and hard-earned lessons of turning our global transit networks into energy-harvesting surfaces. 1. The multi-layered architecture of a solar road. A road that generates power cannot be made of glass alone, it must be a sophisticated sandwich of materials designed to survive millions of tons of pressure while remaining optically clear. The traction layer, the topmost surface, is a high-strength, textured resin or tempered glass. It must provide a friction coefficient equivalent to asphalt to prevent hydroplaning while allowing maximum light transmission to the cells below. The photovoltaic PV layer. Beneath the protective shell lies the engine. Modern designs utilize crystalline silicon or flexible thin film cells. Unlike rooftop panels, these are laid horizontally, necessitating advanced, self-cleaning coatings to prevent dust and grime from obscuring the sun. The electronics and heating layer. This middle tier contains microprocessors and sensors. In colder climates, heating elements use a fraction of the generated power to melt snow and ice, eliminating the need for salt and plows that degrade road surfaces. The base layer, the foundation, transmits the collected energy to the grid or local storage. It also houses the cable corridor, a protected space for fiber optics and utility lines that removes the need for unsightly overhead poles. 2. Dynamic wireless charging in motion power. The true holy grail of solar roads is dynamic wireless power transfer (DWPT). This technology addresses range anxiety by charging electric vehicles (EVs) as they drive. Inductive coils, copper coils embedded beneath the solar panels, create a magnetic field. The receiver, a corresponding coil on the underbody of the EV, picks up this energy through electromagnetic induction, converting it back into electricity for the battery. The result, vehicles can theoretically drive indefinitely without stopping to plug in, allowing for smaller, lighter, and more sustainable battery packs in future cars. 3. Engineering reality. Lessons from the field. The path to solar roads has been paved with challenges. Early pilots, such as the Wattway project in France, provided crucial data on the limitations of the first generation. The durability gap. Heavy freight trucks 18-wheelers exerted forces that cracked early panel designs. Modern 2026-era panels now use hexagonal modularity, which distributes weight more effectively and allows for plug-and-play replacement of single damaged units in minutes. Efficiency trade-offs. Because solar roads lie flat, zero-ring operator tilt, they produce roughly 30% less energy than angled rooftop panels. However, proponents argue that the sheer surface area available, millions of square miles, far outweighs the per-panel efficiency loss. 4. The smart road as a safety hub. Beyond energy, solar roads are active participants in traffic safety. Interactive LED markings. Instead of painted lines, solar roads use embedded LEDs. These can change in real time, widening a lane during rush hour, flashing red to warn of an accident ahead, or illuminating a crosswalk only when a pedestrian is detected. Haptic feedback. Sensors in the road can detect if a vehicle is swerving or if there is debris on the path, sending immediate alerts to autonomous vehicle networks. Summary. Asphalt versus solar roadways. Feature. Traditional asphalt. Solar roadway SR. Primary function. Transport only. Transport plus power generation. Grid impact. 0. Decentralized smart grid. Winter maintenance. Plowing and salt. Internal heating elements. Charging. Gas station, static plug. Dynamic wireless charging. 6. The cryodynamic harvest. Power generation from thermal differentials. In the pursuit of sustainable energy, we often look to the sun or the wind. However, a groundbreaking frontier in thermodynamics explores the power found in the contrast between extremes, the ice electrical generating factory or cryodynamic power plant. This chapter details the concept of a facility designed to extract work from the temperature gradient between ambient sub-zero air and relatively warm, geothermal water. 1. The core principle, thermal gradient extraction. The cryodynamic power plant operates on a modified heat engine cycle. Unlike traditional plants that use extreme heat to create steam, this system leverages the energy potential available when two naturally occurring thermal reservoirs meet in Arctic or subarctic environments. Heat-sourced geothermal water. Even in frozen landscapes, geothermal water often remains at a constant temperature above freezing, e.g., 5-ring operator C to 10-ring operator C. Heat sink. Ambient Arctic air. The surrounding atmosphere provides a vast reservoir of significantly colder air, e.g., -10-ring operator C or lower. The delta T. The plant exploits the difference between these two states to drive phase changes in a working fluid or to initiate mechanical expansion. 2. The internal mechanics, from expansion to electricity. As illustrated in the conceptual schematics, the factory is a vertical stack of specialized chambers designed for high-efficiency energy conversion. Freezing and expansion chambers. Geothermal water is introduced into chambers where it interacts with the frigid ambient air. In some conceptual models, a working fluid with a very low boiling point is used. The warmth of the water causes expansion, while the cold air causes rapid contraction or freezing, creating a reciprocating motion in large-scale expansion pistons. The low-ratio gearbox and transmission. The mechanical energy harvested from the pistons is transferred through a series of massive, synchronized gears. This cryodynamic transmission converts the high-torque, slow-moving expansion strokes into the high-speed rotation required for electrical generation. The electrical generator array. At the apex of the factory, the kinetic energy reaches the generator floor. Here, the rotation is converted into high-voltage electricity, which can be fed directly into the regional smart grid. 3. Integrated water management. A key feature of the ice factory is its circular, fluid management system, ensuring that the geothermal resource is not wasted. Melting tank. After the expansion cycle, any ice formed is routed to a melting tank at the base of the structure. Heating channel. The melting process is often assisted by the incoming geothermal flow, which pre-cools the water for the next cycle while recycling the thermal energy to reliquefy the ice. Exhaust. Cold air used for the freezing process is expelled via a cold exhaust system, ensuring the internal temperature of the plant remains optimized for the cycle. 4. Environmental and industrial synergies. The ice electrical generating factory represents a passive-active hybrid of industrial design. By being located in mountainous or permafrost regions, the structure itself acts as a giant radiator. Component. Function in the concept. Ambient air intake. Harnessing natural -10-ring operator C air as a free coolant. Geothermal inlet. Utilizing 5-ring operator C water as a stable, renewable heat source. 7. The informed outlet. Empowering energy awareness at the point of consumption. The journey toward energy efficiency often begins with awareness. For too long, electricity consumption has been an abstract concept, aggregated into a single, inscrutable monthly bill. This chapter introduces the informed outlet, a deceptively simple yet profoundly powerful innovation that places real-time energy metering directly at the point of consumption, empowering users to become active participants in managing their electrical footprint. 1. The transparency imperative. Why real-time matters. Traditional energy meters measure whole home consumption. While smart meters offer some granular data, they rarely pinpoint the energy appetite of individual devices. The informed outlet addresses this black box problem by providing immediate, device-specific feedback. Behavioral economics. Studies show that immediate feedback on consumption leads to significant behavioral changes. Seeing 0.005 kWh and $0, as in the image, for a currently idle device, versus rapidly accumulating numbers for a power-hungry appliance, creates a direct link between action and consequence. Targeted efficiency. Instead of guessing which appliances are draining power, users can now precisely identify energy vampires, devices drawing power even when off, or inefficient appliances. This knowledge enables informed decisions about upgrades, repair, or changed usage patterns. 2. Anatomy of the informed outlet. The elegance of the informed outlet lies in its seamless integration. It looks and functions like a standard electrical receptacle but incorporates sophisticated metering technology. Integrated current transformer (CT) sensor. A miniature CT sensor within the outlet detects the electromagnetic field generated by the current flowing to the plugged-in device, providing precise amperage readings. Voltage sensing. A built-in voltage sensor, combined with the current reading, allows the outlet to calculate instantaneous power, watts, and accumulated energy, kilowatt-hours, kWh. LCD or e-ink display. A low-power display, like the green-on-black LCD shown, provides clear, unambiguous data on usage and estimated cost. E-ink displays offer even lower power consumption and better readability in varying light. User interface (UI). A simple button or touch-sensitive area allows users to activate the meter display, cycle through different metrics, e.g., instantaneous watts, cumulative kWh, estimated cost, or reset the accumulated usage for a new monitoring period. Programmable tariffs. Advanced models allow users to input their local electricity tariffs, e.g., peak versus off-peak rates, providing accurate real-time cost estimations. 3. Beyond the display, connectivity and smart home integration. While a standalone display is valuable, the informed outlet truly shines when integrated into a broader smart home ecosystem. Wireless connectivity (Wi-Fi, Zigbee, Z-Wave) enables outlets to communicate data to a central hub, smartphone app, or cloud platform. This allows for remote monitoring, historical data logging, and comparative analysis of device consumption over time. Automated action triggers. Imagine an app notifying you that your old refrigerator is using excessive power, or a smart plug automatically turning off the phantom load from your entertainment system at bedtime. Energy audits on demand. A user could initiate a home energy audit from their phone, receiving a detailed breakdown of consumption by each plugged-in device without needing specialized equipment. Grid response. In a truly smart grid, these outlets could potentially receive signals to reduce power to non-essential devices during peak demand periods, contributing to grid stability and potentially earning the user credits. 4. Impact on behavior and sustainability. The informed outlet moves beyond mere data reporting. It becomes a catalyst for sustainable living. Education. It demystifies electricity, teaching users about the consumption habits of their devices. Empowerment. It provides agency, allowing individuals to make informed choices that reduce their energy bills and environmental impact. Scalability. When rolled out broadly, millions of informed outlets could collectively contribute to significant reductions in energy demand, alleviating strain on power grids and reducing the need for new, carbon-intensive generation. 8. Can you write a chapter on the concept of sealing high-voltage wires for protection against live wire scenarios, electrocution, and also possibly reducing the live wire area of power if the wire was to fall on the ground? 8. Precision recovery. Mechanical systems for screw head restoration. In mechanical assembly and maintenance, one of the most persistent sources of downtime is the stripped or damaged fastener. When the drive geometry of a screw head, be it Phillips, Torx, or hex, is compromised by over-torquing or corrosion, standard removal tools become ineffective. This chapter examines the engineering behind active recutting tools (ART), specifically focusing on portable devices designed to mechanically reshape and restore the structural integrity of a damaged screw head. 1. The mechanics of head deformation. Screw heads typically fail when the stress applied by a driver exceeds the material's yield strength, causing the internal walls of the drive to round out. A damaged head prevents the driver from achieving the necessary mechanical interlock, leading to further slippage and material loss. The screwed head rescue innovation addresses this by treating the damaged fastener not as junk, but as a workpiece to be remachined in situ. 2. Design and functional architecture. The recovery device is a self-contained, handheld machining unit designed for precision and high torque. Key components include the activation interface. A high-visibility activate button allows the operator to engage the internal drive system once the tool is properly seated over the target fastener. The cutting reshaping wheel. The core of the device is a hardened, serrated rotary wheel. This wheel is engineered to bite into the compromised material of the screw head, carving new, sharp edges that provide fresh purchase for extraction tools. Internal gear train. To generate the force necessary to reshape industrial-grade steel fasteners, the device utilizes a compact, high-ratio internal gearbox. This system amplifies the input power to the cutting wheel, ensuring a consistent and powerful reshaping action. Adjustment housing. The lower machine assembly is designed to descend and envelop the damaged head, centering the tool to ensure the new geometry is perfectly aligned with the screw's vertical axis. 3. Procedural application. The rescue cycle. Restoring a fastener involves a three-stage mechanical process. Centering and stabilization. The tool is placed directly over the damaged screw. The housing ensures that the cutting wheel is positioned at the exact center of the deformation. Material reprofiling. Upon activation, the lower machine components engage. The rotary wheel rotates against the damaged surfaces, removing burrs and rounding and reshaping them into a defined, usable drive geometry. Extraction. Once the head is reshaped, the device is removed, leaving behind a clean, sharp profile that can once again accept a standard driver for removal or further tightening. 4. Innovation impact in maintenance and repair. The ability to repair rather than drill out a screw has significant implications for industrial efficiency. Traditional method. Screwed head rescue method. Drilling extraction, high risk of damaging the surrounding material or internal threads. Reshaping, preserves the fastener's body and the integrity of the host material. Time intensive, often requires multiple steps, specialized bits, and cleanup of metal shavings. Rapid, single-step activation restores the head in seconds. Destructive, the fastener is destroyed and must be replaced. Restorative, occasionally allows the existing fastener to be salvaged or easily removed. 9. Harmonic harvest, oscillating wave energy converters in coastal infrastructure. As global energy demands shift toward decentralized and renewable sources, the blue economy has emerged as a critical frontier. While offshore wave farms capture the immense power of the open ocean, the Harmonic Coastal Converter (HCC), specifically designed for integration with existing jetties, piers, and bridges, offers a pragmatic solution for localized power generation. This chapter explores the mechanical synergy between maritime infrastructure and the rhythmic energy of moderate coastal waves. 1. Structural integration, the parasitic power model. Integrating wave energy converters directly into existing structures like jetties or bridges significantly reduces the capital expenditure of ocean energy. Rather than building standalone offshore platforms, the HCC utilizes the robust pilings of coastal infrastructure as its primary support. Linear piston array. As seen in modern pier-side installations, a series of buoyant floats are attached to the underside of the bridge deck via vertical piston arms. Stable mounting. The bridge provides a fixed, stable platform that allows the converters to operate without the complex mooring systems required by floating offshore arrays. Protection from extremes. The bridge deck acts as a natural shield, protecting the mechanical gearbox and electrical dynamos from direct rain and salt spray, while the floats remain in the active wave zone. 2. The physics of rhythm power. Moderate waves, while less energetic than deep-sea swells, offer a high level of periodicity, a consistent rhythm that can be mechanically harvested. Oscillation. Ocean waves provide vertical displacement. As a wave crest passes, it lifts the buoyant float. As the trough follows, gravity pulls the float back down. Mechanical translation. This reciprocating vertical motion is transferred up the piston to a rotary dynamo or a hydraulic motor mounted under the bridge. Inertial management. During storm events where wave height exceeds safe operational limits, the system can utilize move inertia protocols to lock the floats in a raised position or decouple the dynamos to prevent mechanical failure. 3. Electrical conversion and localized grids. The energy captured by the HCC is typically converted and managed in situ, making it ideal for powering coastal amenities. The dynamo system. The rhythmic movement of the floats raises and lowers an internal dynamo, generating an alternating current AC. Bridge amenities. A single array of converters under a standard jetty can generate enough power to support the bridge's own lighting, emergency intercoms, and the informed outlets discussed in previous chapters. Smart grid feeding. Excess power is routed through armored conduits to onshore substations, providing a consistent baseload of renewable energy for coastal communities. 4. Environmental and aesthetic considerations. Unlike large wind turbines, jetty-integrated wave converters have a low visual and environmental profile. Feature. Impact benefit. Visual footprint. Hidden beneath the bridge deck, maintains the coastal skyline. Marine life. Low-frequency movement is generally non-disruptive to local fish populations. Coastal protection. By absorbing wave energy, the converters can actually reduce the scour or erosion force hitting the bridge pilings. Noise pollution. Submerged mechanical parts dampen the sound of operation. 10. Decentralized energy autonomy. The human-powered pedal dynamo. In an increasingly electrified world, the ability to generate power independent of a centralized grid is a cornerstone of resilience. While solar and wind are dominant, they are dependent on environmental conditions. This chapter examines the manual kinetic energy harvester (MKEH), a high-efficiency pedal-driven dynamo system designed for rapid battery charging through human mechanical work. 1. The physics of human-centric power. The MKEH transforms the mechanical energy of a rotating pedal arm into electrical energy via electromagnetic induction. The system is built on the principle that human legs are significantly more powerful and have greater endurance than human arms, making a pedal-based system the optimal choice for manual generation. Torque and leverage. The efficiency of the system is heavily influenced by the length of the pedal arm. A longer arm increases the mechanical advantage leverage, making it easier for the operator to maintain the high RPMs required for effective charging. The dynamo core. Inside the chassis, the rotating pedal arm drives a high-efficiency dynamo. As the internal magnets spin relative to the copper windings, they induce a current that is then stabilized and regulated for battery storage. 2. Functional architecture of the MKEH box. The device is engineered as a rugged, portable power station. Its design focuses on durability and ease of use in field conditions. High-torque pedal interface. The orange anodized pedal arm is designed for maximum structural rigidity to prevent energy loss through flex. The folding pedal allows for compact storage while providing a wide, grippy surface for the foot. Voltage regulation and output. The box features dedicated positive and negative terminals, alongside a standard DC jack, allowing it to charge a wide variety of battery chemistries and portable electronics. Thermal management. The lower half of the chassis features integrated cooling fins, heat sinks to dissipate the heat generated by the dynamo during extended charging sessions. Visual feedback. The top surface includes a high-contrast LED indicator, the lightning bolt symbol to signal active charging and the health of the internal generation circuit. 3. Efficiency ratios and performance. Human-powered generation is a test of sustained metabolic output. The MKEH is optimized to capture as much of that output as possible. Parameter. Specification. Benefit. Arm length factor. The longer the pedal arm, the easier and faster the charging. Input type. Kinetic rotational. Output versatility. DC jack and raw terminals for diverse battery types. Durability. Reinforced corner bumpers for high impact resistance in transport. 4. Use cases. Beyond the emergency. While the MKEH is an essential tool for disaster relief and emergency kits, its applications extend into several specialized fields. Remote field research, powering sensors and laptops in deep wilderness locations where solar is obstructed by canopy cover. Micro-entrepreneurship, providing a charging as a service model in off-grid communities. Fitness integration, coupling the necessity of energy generation with daily exercise routines, creating a tangible reward for physical activity. Conclusion. The human as a renewable resource. The pedal dynamo box serves as a bridge between human biology and electrical technology. 11. Elevated safety. Dielectric pedestals for ground fault survival. In the immediate aftermath of a high-voltage line failure, the ground surrounding a power pole can become a lethal zone of electrical potential. While previous chapters focused on containing the wire, this chapter explores a secondary, human-centric defense mechanism, the Integrated Dielectric Safety Pedestal (IDSP). This innovation provides a permanent, non-conductive, safety island around the base of utility poles, designed to prevent electrocution through step potential. 1. The physics of the lethal circle. When a live wire contacts the ground or a utility pole, current flows into the earth, dissipating outward in concentric circles. The gradient effect. The voltage is highest at the point of contact and decreases as it moves outward. Step potential danger. If a person walks within this zone, their feet can bridge two different voltage levels. This potential difference causes electricity to flow up one leg and down the other, often with fatal results. The pole as a conduit. Even if the wire hasn't snapped, a lightning strike or equipment failure can energize the pole itself, creating a high voltage zone at its base. 2. Design of the dielectric pedestal. The IDSP is a structural, non-conductive platform encircling the utility pole, providing a safe harbor for pedestrians caught in a fault zone. Advanced dielectric materials. The platform is constructed from high-density, wood-textured polymers or fiberglass reinforced plastics (FRP) that possess extremely high dielectric strength. These materials ensure that no current can flow from the energized ground into the platform. Raised clearance. The pedestal is elevated several inches off the ground. This physical air gap provides an additional layer of insulation, ensuring there is no direct path for current even if the ground is saturated with water. Non-slip topography. To prevent secondary injuries from falls during a panic, the surface features a high traction, wood-grain texture that remains effective in rain or ice. 3. Procedural safety. The jump to safety protocol. The IDSP is designed to be used in emergency, wire-down scenarios. If a pedestrian sees a fallen wire or hears the buzzing of a ground fault, the pedestal serves as a designated, safe zone. The leap. If already near the pole, the pedestrian should leap with both feet together onto the pedestal. Keeping feet together prevents the body from bridging two different voltage points during the jump. Isolation. Once on the platform, the individual is electrically isolated from the earth. Wait for de-energization. The individual must remain on the pedestal until emergency services or utility crews confirm that the line has been de-energized and the ground is safe to traverse. 4. Urban integration and implementation. The IDSP is designed to blend into the urban environment, appearing as a standard piece of street furniture or a tree protection grate. Feature. Engineering benefit. Circular geometry. Provides 360-degree access for a quick leap from any direction. Material durability. UV resistant and chemical resistant for a 50-year service life. Visual indicators. Can be outfitted with glow-in-the-dark or reflective markings for nighttime visibility. Secondary use. Acts as a barrier to prevent vehicle or lawnmower impact on the pole base. 12. Structural discontinuity. Self-extracting breakaway pylons and tension suspension systems. One of the most common causes of localized grid failure and public danger is the pole strike incident, typically caused by vehicle collisions. In traditional infrastructure, a pylon is a rigid, monolithic column. When the base is struck, the entire structure often topples, bringing thousands of volts of live wire down with it. This chapter introduces the sacrificial base pylon (SBP), a design that intentionally detaches upon impact while maintaining the electrical grid's elevation through tension-based suspension. 1. The concept of the floating pylon. The SBP system reimagines the utility pole not as a rigid beam, but as a multi-part assembly designed to fail safely. The innovation relies on the principle of structural discontinuity. Intentional extraction. The bottom section of the pylon, the collision zone, is designed to be easily extracted or severed upon a high-energy impact, such as a car crash. The suspension bridge analogy. Instead of the pole supporting the wires, in a failure event, the wires support the pole. The upper segment of the pylon remains suspended in the air, held up by the longitudinal tension of the transmission lines and the strength of the adjacent, UN-struck pylons. 2. Engineering the breakaway interface. For a pylon to float after an impact, the connection between the base and the upper mast must be precisely engineered. Shear bolt connectors. The pylon is joined at approximately 1.5 to 2 meters above the ground using high-precision shear bolts. These bolts are designed to snap only when a specific lateral force is applied, the force of a vehicle, allowing the lower section to move without dragging the upper mast down. Lightweight composite masts. To ensure the wires can support the weight of the remaining pylon segment, the upper mast is constructed from high-strength, lightweight carbon fiber or reinforced polymers rather than heavy timber or concrete. Dampening tether. A central, non-conductive safety cable dielectric tether inside the pole prevents the suspended segment from swinging wildly, providing a controlled, drip effect that keeps the live wires at a safe height above traffic. 3. Maintenance and rapid recovery. The extractable nature of the base allows for significantly faster repairs compared to traditional utility poles. Collision event. A vehicle strikes the base, the shear bolts snap, the lower section is knocked away while the upper section floats above the car. Grid integrity. Because the wires never hit the ground, there is no live wire scenario for pedestrians or the driver. The plug-and-play repair. Utility crews arrive to find the upper mast intact and suspended. They simply slide a new base section into the foundation, lower the upper mast back onto it, and replace the shear bolts. The grid remains active throughout the entire repair process. 4. Safety performance comparison. Feature. Standard utility pole. Self-extracting pylon (SBP). Impact result. Total collapse, wire down scenario. Base extraction, suspended pylon. Public danger. High risk of electrocution, fire. Low, wires remain at safe height. Repair time. 6 to 12 hours requires new pole. 1 to 2 hours requires base swap. Vehicle safety. Pole acts as a brick wall, high G-force. Base yields lower G-force impact. Trolley on tracks, the low center gravity galley rail system. In the high-stakes environment of commercial aviation, the cabin aisle represents a unique logistical challenge. For decades, the standard service trolley has relied on manual guidance and friction-based braking, leaving it vulnerable to the unpredictable forces of high-altitude turbulence and human error. This chapter introduces the Integrated Cabin Track and Low-Profile Service Array (ICT), a structural innovation designed to lock the service experience into a path of total stability. 1. The engineering of stability. The ICT system replaces the traditional top-heavy meal cart with a modular tray system anchored to a recessed floor track. This design addresses two primary safety concerns. Turbulence anchoring. During sudden clear air turbulence, unrestrained carts can become dangerous projectiles. The ICT, tray on tracks, is mechanically coupled to the aircraft floor. Even during severe vertical acceleration, the service unit remains firmly attached to the airframe. Low center of gravity. By utilizing a minimalist, open-frame stainless steel chassis rather than a bulky enclosed box, the center of gravity is significantly lowered. This reduces the tipping moment that occurs when a cart is pushed around a corner or caught in a sudden jolt. 2. Precision guidance and human error mitigation. Human error, ranging from forgotten brake engagement to spills during handoffs, is a major contributor to cabin injuries. The ICT system automates several safety checks. Self-locking track interface. The wheels of the service array are designed to lock into the track whenever the attendant releases the handle. This ensures that the cart cannot run away if the attendant is distracted or if the aircraft tilts unexpectedly. Modular spill containment. Unlike traditional flat-top carts, the ICT utilizes recessed tiers. Each meal tray is nested within a raised edge frame, preventing beverages or hot food from sliding off the unit during minor vibrations or uneven pushing. 3. Efficiency and aisle dynamics. Beyond safety, the ICT system optimizes the limited space of the modern aircraft cabin. Narrow profile design. Because the track provides the lateral stability, the cart itself can be narrower, allowing more room for passengers in their seats even when service is in progress. Automated docking. The track leads directly into the galley, allowing for a plug-and-play reloading process. Spent arrays are rolled into a docking port where they are automatically secured for descent or heavy weather. 4. Comparison of service modalities. Feature. Standard manual cart. Integrated cabin track ICT. Stability mechanism. Manual friction brake. Mechanical rail coupling. Turbulence response. Potential for lift projectile. Structural anchoring to airframe. Center of gravity. High top heavy. Low open frame design. Guidance. Human steering. Precision rail guidance. 14. Priority path. GPS integrated traffic preemption for emergency response. In the critical minutes following an emergency call, the primary obstacle to saving lives is often the urban grid itself. Traffic congestion and red light cycles create significant delays for first responders. This chapter examines Priority Path Technology (PPT), a sophisticated mobile and GPS-linked system that allows police, fire, and ambulance services to communicate directly with traffic infrastructure to clear their route in real time. 1. The anatomy of traffic preemption. Priority Path Technology moves beyond simple sirens and lights, which rely on the cooperation of other drivers. Instead, it uses a digital handshake between the emergency vehicle and the city's traffic management system to ensure a green corridor. The mobile command gadget, as shown in the conceptual interfaces, responders use a dedicated handheld or dash-mounted device. This gadget serves as the bridge between the vehicle and the traffic light. GPS-triggered activation. The system can be set to auto path mode. Using the phone's high-precision GPS, the device calculates the vehicle's trajectory and automatically sends a signal to upcoming intersections to switch lights to green before the vehicle even arrives. Manual override. The remote. For unpredictable situations, such as navigating around an accident, the responder can manually activate the green request via a physical button on the remote, providing immediate control over the nearest signal. 2. Hierarchical prioritization. The Life First protocol. One of the most innovative features of the PPT system is its ability to distinguish between different types of responders. Not all emergencies carry the same time sensitivity, and the system manages the grid accordingly. Level 1, Ambulance. Highest priority. Because medical emergencies often have the narrowest, golden hour, for survival, ambulances are granted the highest tier of access. If an ambulance and a police cruiser approach the same intersection from different angles, the system prioritizes the ambulance's path. Level 2, Fire services. Due to the weight of the trucks and the potential for rapid fire spread, fire engines are granted high priority to maintain momentum. Level 3, Police response. While critical, police vehicles are often more nimble. They receive priority over civilian traffic but yield to medical or fire emergencies within the system's logic. 3. Integrated visual feedback. The system provides real-time confirmation to the driver, ensuring they know exactly when the infrastructure has responded to their request. In Car HUD, the mobile gadget displays the status of the upcoming light, e.g., SEO, or signal engaged status. Confirmation lighting. A specific LED pattern on the traffic light itself, visible only to the responder, confirms that the preemption request has been accepted and the cross-traffic has been safely halted. 4. Impact on emergency outcomes. Metric. Traditional response. PPT-enabled response. Average delay at lights. 45 to 90 seconds per major intersection. Less than 5 seconds. Maintained momentum. Collision risk. High. First responders, clearing, red lights. Low. Controlled green light transition. Travel time consistency. Highly variable based on traffic. Highly predictable and optimized. Operational stress. High for the driver navigating gridlock. Lower. Focus shifts to safe driving.